Hi. In the last few lectures, we've been looking at JASP and how it can do graphics. We've been working on a particular data set. I want to go ahead and reopen that data set. So I'm going to go to Open, Data Library, and go to Descriptives. And here under Descriptives, there's a data set called Sleep. That's what I've been using in my first few lectures. It automatically comes up with some information on its own. And I'll just use this as a reminder that we basically have 10 people, and they the experimenters recorded their sleep on a control night. Then they used one type of drug and looked to see how much extra sleep they got. So extra is the added number of hours over their control. And then they tried another night with another type of drug. And it looks graphically as though that second drug did better. The average looks like it's higher, but is it significantly higher? So we have this divided up into two groups, and so we can do a t-test. And so I want to do my introduction to t-test. So we're going to do t-test, and we're going to go ahead and do this as an independent samples t-test. Now, to do that, we're going to basically go and take our dependent variable, extra hours of sleep, and put it under dependent variables. We're going to take group and stick it in as the grouping variable. And automatically it produces the t-test result without much fanfare, without much added information. And the p-value is 0.079. We typically set alpha. Alpha refers to a particular p-value at 0.05. I'll talk more about that as I put in more information here. But this would be considered not statistically significant because the p-value needs to be below 0.05 to be significant. Let's add in more, and then I'll come back to that. So I want to go ahead and add in the location parameter. I'm going to go ahead and add in effect size. Most importantly, I'm going to add in descriptives because to me it's just silly to be looking at this without the descriptives. So the descriptives basically tell you you have two groups. It's treating these as two independent groups, and they're not actually truly independent. It's the same people in each group. And so you could argue that that's a violation of what's called the independence assumption, but it's not the type of violation that I really would worry about. What I would really worry about is if you violated the independence assumption by taking the same people and are people who were all part of a group and sticking them in the same group. But here we have everyone in one group and then everyone in participating again in another group. And the independent groups t-test is going to be overly conservative in that case, not overly liberal. And what that means is that the likelihood that I'm going to reject the null hypothesis, that is, claim that there's a difference between these two groups when there's actually not a true difference between the two groups, I'm treating that as a conservative judgment. In other words, I'm not going out on a limb to claim that there's a difference. So I'm making it to where I'm less likely of making what you might call a false positive. So to remind you of what's in here, we have the people with the second drug sleeping 2.33 hours. The people with the other type of drug sleeping only 0.15. If you take that 0.75 minus the 0.233, you get a mean difference of minus 1.58. So there's a 1.5 hour difference between the two groups, which would seem to be kind of sizable. When we look at our Cohen's d, a Cohen's d of around 0 would indicate there's no effect. A Cohen's d of around 0.2 would indicate that there's a small effect. A Cohen's d of around 0.5 would indicate that there's a medium effect, and a Cohen's d of 0.8 and above would indicate that there's a large effect. So this Cohen's d is kind of a rule of thumb indicator that this mean difference that looks sizable. I mean, I'd say an hour and a half of extra sleep is a lot. And this is saying, yeah, it's a big difference. But the sample size is small. There's only 10 people in each condition. And with only 10 people in each condition, even though you have a large effect, it can come out not statistically significant. Now that P of 0.079 is basically the probability of making a type 1 error. A type 1 error is if I say that there is a difference between the two groups, that the second drug works better than the first drug, and I'm wrong, that the probability of being wrong in that claim, given these data, is about 7.9%. And that's a little bit higher than what we traditionally allow. So what the field traditionally allows is just to go up to an error of about 0.05. So this is probability of making a type 1 error. Type 1 error, it's bad to make errors. So that's a little bit too much. I want it to be 0.05 or less. So I'm going to say it's non-significant. And if I say it's non-significant, then if that's my claim, then there's no longer a problem with the type 1 error. I could be making a type 2 error, that is a false negative. That is, it could be that there really is a true difference as indicated by that large Cohen's d, but I don't have enough people. So what I should do is when I see a Cohen's d that's large and I have a small n, I should basically not stop. I should go ahead and collect more data and see if the effect holds as my sample size increases. Let's see what else we can see here. It'll also give us descriptive plots showing us that here's the mean difference between the two groups. It will give us rain cloud plots. These are similar to some of the plots that we've seen. The rain cloud is basically showing you here's the individual data points for people, how much extra sleep the first group got, first drug condition versus the second drug condition. Here it's shown as a box and whiskers plot with the median value being higher for the second drug condition than the first drug condition. And here is a density curve. It's a version of a histogram, but it's basically smooth. It's kind of a smoothed out version of a histogram projecting what the smoothed out distribution would look like based upon the data that we have. And the golden sand area is showing what's common to both distributions. So both distributions have a lot in common. The salmon colored or sort of pinkish looking color is basically showing how the second drug condition, that distribution is sticking out a little bit higher than is the other distribution. And the green is showing us that it's going out a little bit, that drug condition is peaking out a little bit lower than what the two distributions have in common. So you have evidence visually suggesting that there's a significant difference, but you have to look at the test, and that is not passing our bar, and so you really need to have a larger sample size. Now, one other thing that I want to point out is that the way that we set up the alternative hypothesis was to basically not make any assumptions about which drug would do better, which for me in this case, that makes a lot of sense because I know nothing about these two drugs. I'm just borrowing the data set from online. I don't know why one drug would be better than the other, so it makes perfect sense that I should stick with that. Let's say that there was a good reason while I should expect theoretically and based upon previous evidence that drug 2 was doing better than drug 1, then I could have made my alternative hypothesis and that would give me extra power. And you notice that my p-value does now come in under the 0.05. And so if I had the theory and prior evidence to back me up, and I had specified this in advance, that's important, not just looking at the data and saying, oh, that's not good enough, but in advance, then had I done it that way, you'll notice that I would have had the power to go ahead and claim, even though it's exactly the same t-value, that that probability value is significant. So I think I will halt it there, and that's your independent samples t-test, and we'll have more to say about this data set in upcoming videos. Thanks much.